Okay, let's just dive right into this. You know that magic metal box sitting under the hood of your car? We just turn a key or hit a button, and boom, we're suddenly flying down the highway. But what is actually happening in there? Welcome to our explainer. Today, we're taking a seriously deep dive into the completely fascinating and honestly explosive world of the internal combustion engine.
150. That is exactly how many contact hours engineering students spend grinding through the dense, rigorous curriculum of Course U-105, Automobile Power Plant. We're going to take that entire 150-hour syllabus and just compress it. We're compressing it into a single, engaging, bite-sized visual journey. It's basically the ultimate speedrun of an engineering degree, giving you all the pure mechanical genius underneath with zero filler.
So here's our semester syllabus for today. First up, anatomy of an engine. Second, the science of combustion. Third, fuel supply and injection. Fourth, lubrication and cooling. And finally, number 5, the final exam. Let's get to work. Part 1, anatomy of an engine. Okay, before we start sparking any explosions, we really need to understand the mechanical skeleton holding this incredible machine together. I want you to think of the engine exactly like a biological organism. Every body needs a skeleton and muscles, right? Well, here's ours. The cylinder block? That's your rib cage, the absolute solid foundation of it all. Inside, the piston acts like a pumping heart muscle, driving up and down. That piston connects to the connecting rod, which is basically an arm, pushing down on the crankshaft. And that crankshaft is essentially the spine, translating that up and down pumping motion into the rotational spin that actually turns your wheels. And up top, you've got the valves and camshaft acting just like lungs, perfectly timing when to breathe in fresh air and exhale exhaust. It is literally a masterpiece of mechanical harmony. Now, you're going to hear some intimidating engineering jargon thrown around in the automotive world, but let's demystify one right now. Swept volume. Sounds super complicated, right? It's really not. Just imagine our piston at the absolute top of its stroke, that's top dead center, traveling down to the very bottom, or bottom dead center. The physical space it sweeps through, the air it actively displaces during that single downward motion, is the swept volume. It's simply the breathing capacity of that cylinder. And that brings us to the great divide in the engine kingdom. SI versus CI, spark ignition against compression ignition. In a standard petrol engine, you have a literal spark plug that zaps the air-fuel mixture to create an explosion. That's your SI engine. But diesel engines, they're CI, compression ignition. They don't use a spark at all. Instead, they squeeze the air so incredibly hard, creating so much intense pressure and heat that the fuel just spontaneously combusts. Part 2, the signs of combustion. All right, I want you to mentally speed up here, because inside that cylinder, things get fast, violent, and highly explosive. This is where the physical skeleton actually comes alive. But for this explosion to happen perfectly, without destroying the block, we need a precise chemical heartbeat. Enter the stoichiometric ratio. This isn't just some fancy chemistry term, it's the exact, perfectly balanced recipe of air and fuel needed to burn everything cleanly without leaving a single molecule behind. If your engine hits this ratio, it hums. But if this delicate balance gets thrown off, well, things get really chaotic. First, we have detonation. This is when the unburned mixture at the edge of the cylinder suddenly and violently explodes all on its own, crashing against the main flame front. It's a localized, highly destructive shockwave that hits your engine block like a literal hammer. Then there's pre-ignition. This is a massive threat specifically to spark ignition engines. Imagine a glowing hot spot inside the cylinder, maybe some leftover carbon buildup. It gets so hot that it ignites the fresh fuel mixture before the spark plug even gets a chance to fire. The engine is trying to push the piston up, but this premature explosion is violently forcing it back down. And we definitely can't forget diesel knock. Since diesel engines rely purely on pressure, if the fuel doesn't ignite exactly when it's injected, it pools up. When it finally does ignite, all that pooled fuel explodes at once in a massive, uncontrolled pressure spike. It's a wildly unique, violently loud problem for compression ignition engines. So, what actually happens when combustion goes wrong? Well, we've just seen it. Shockwaves, premature explosions, and severe physical stress. Left unchecked, these abnormal combustions will literally melt pistons and shatter the engine block, which tells us something absolutely crucial. Our engine needs a hyper-regulated way to eat and an incredibly powerful immune system to protect itself. Part 3, fuel supply and injection. If the cylinder is the heart, this system is the digestive tract, precisely measuring and delivering the crucial energy needed to feed the muscles. But we have to grade the food our engine eats. We hear these terms at the gas station all the time, right? Octane rating is for petrol engines. It literally measures the fuel's ability to resist those dangerous early explosions or NOx we just talked about. Cetane rating, on the other hand, is for diesel fuel. It measures the exact opposite, how quickly and willingly the fuel ignites under pressure. Two completely different digestive requirements for two very different systems. Let's actually trace the journey of a single drop of fuel. It starts in the fuel tank. From there, a feed pump pushes it forward, forcing it through primary and secondary filters to strip out any microscopic dirt. Then it hits the injection pump, maybe a high-tech common rail diesel system or a multi-point petrol injector. Finally, it reaches the injector nozzle, where it's sprayed as a superfine, highly pressurized mist directly into the violent chaos of the combustion chamber. To hit course outcome 4 of the syllabus, we absolutely have to compare the two. Notice the stark contrasts here. Petrol systems traditionally use carburetors or multi-point fuel injection, rely on a spark plug, and care deeply about octane. Diesel systems demand heavy-duty injection pumps, rely strictly on high compression, and are graded by cetane. Understanding this breakdown means you understand the fundamental split in modern automotive engineering. Part 4. Lubrication and cooling. Let's slow the pace down a bit. With all those explosions and all that intense metal-on-metal friction, without a biological immune system, this engine would melt itself into a block of useless slag in a matter of minutes. We have to keep its vital components from grinding to dust. We do this through some seriously ingenious lubrication systems. Some smaller engines just mix oil directly with the fuel. That's the petrol type. Others use a splash system, literally scooping and throwing oil all around the crankcase. Most modern cars, though, use a force feed system, pushing highly pressurized oil right into the bearings. And depending on performance needs, that oil is stored right under the engine in a wet sump, or pumped to a completely separate tank in a dry sump. And of course, all this oil is carefully graded by SAE viscosity and API performance standards to ensure it flows perfectly at any temperature. But oil only handles the friction. What about the explosive heat? We have two primary methods of temperature regulation. Air cooling, where heat dissipates through metal fins as wind rushes past. You see this a lot on motorcycles. And water cooling, which is a system in most cars, where a water pump pushes liquid through the engine jacket, capturing heat and sending it to the radiator to cool down, all regulated by a thermostat. But beware, while overheating is famous for destroying engines, overcooling is just as much of a hazard, drastically lowering engine efficiency and increasing wear. It's a delicate balance. Part 5. The final exam. Well, congratulations, you've survived a massive speed run of course AU 105. We've gone from the cold iron of the cylinder block, straight through the fire of combustion, mapped the fuel lines, and finally cooled it all down again. To prove just how far you've come, take a look at this. This is an actual 5-mark question pulled straight from the semester end examination of the syllabus. Draw a neat diagram of a dry sump system and compare with the wet sump system. Before this explainer, that might have sounded like total alien terminology, but now, you know exactly what it means, why the engine needs it to survive, and how it fits into the grand, complex biology of the automobile power plant. So the next time you turn the key and hear that engine roar to life, ask yourself, is it running in perfect stoichiometric harmony, or is it a split second away from detonation? Keep questioning the world under the hood, and I'll catch you in the next explainer.